Right now, at this very moment, you are hurtling through one of the largest known structures in the entire observable universe. It is not a star, not a galaxy, not even a cluster of 1,000 suns burning together. It is an absence, a colossal hollow region of space where almost nothing exists. You have been inside it your entire life, and so has every human who has ever lived before you. And the most unsettling part is that almost nobody ever mentions it at the dinner table. Scientists know about it, cosmologists debate it, and yet it rarely makes the headlines the way black holes or Mars missions do. It sits there, vast and invisible, quietly surrounding everything you have ever known. We are traveling through a cosmic void, and that fact alone should stop you cold. The journey begins right here, in the emptiness we call home. Most people picture the universe the way an old textbook might show it, stars scattered like salt grains across a dark, even cloth. That image is clean, intuitive, and almost completely wrong when you zoom out far enough. At the largest scales, the universe does not look like a uniform sprinkle of light at all. Instead, it resembles something closer to a three-dimensional spiderweb, suspended in absolute darkness, glowing faintly at every intersection. Galaxies and their clusters are not spread evenly through space, but are packed tightly into long, luminous threads called filaments. These filaments stretch across hundreds of millions of light years, weaving together into what astronomers call the cosmic web. Between those glowing threads lie the voids, enormous hollow regions where matter is dramatically scarce. The contrast between these two zones, the dense filaments and the empty voids, is one of the most striking features of the universe at its grandest scale. It is a structure so enormous that the human mind genuinely struggles to hold it. Here is the part that tends to surprise people when they first hear it stated plainly and directly. Those voids, those hollow regions between the cosmic filaments, are not minor gaps or thin corridors of emptiness separating the busy parts. They're the dominant feature of the universe by volume, accounting for something in the range of 90% of all the space that exists. The filaments and walls where galaxies cluster and stars burn are, in the grand accounting of space, almost a footnote. Most of the universe is simply nothing, or close enough to nothing that the difference barely matters on a cosmic scale. The matter, the galaxies, the stars, the dark matter halos, all of it is compressed into a thin scaffolding stretched across an ocean of void. Think about that the next time someone tells you the universe is full of wonders. It is mostly full of an extraordinary, humbling emptiness. And we're living inside a piece of that emptiness right now. Our galaxy, the Milky Way, sits inside a region of space that astronomers have been studying with growing intensity and growing unease. This region is known by two names that both carry the same quiet weight of strangeness. Some call it the KBC Void, named after the researchers Keenan, Barger, and Cowie who studied it carefully and published their findings. Others simply call it the local hole, a name that is blunter but perhaps more honest about what it actually is. According to the hypothesis built around this structure, our galaxy is not located in a typical, average stretch of the cosmic web. Instead, we appear to be sitting inside a vast underdensity, a region where the concentration of matter is noticeably lower than the cosmic average. It is as if the universe built a sprawling, quiet neighborhood far from its busiest districts, and somehow the Milky Way ended up parked right in the middle of it. The local hole is not a small feature on the cosmic map. By some estimates, it could stretch roughly 2 billion light years from one side to the other. 2 billion light years is a number that deserves a moment of honest silence, because it does not fit neatly into human intuition. For comparison, the entire observable universe spans roughly 93 billion light years in diameter, which is already incomprehensible. The KBC Void, at 2 billion light years across, would represent a significant fraction of the cosmic neighborhood we can actually study and measure. Inside this region, the density of matter, the galaxies, the clusters, the dark matter threading through everything may be measurably lower than what you would find in a typical patch of the universe. The filaments and walls that define the cosmic web exist out at the edges of this void, surrounding it like the dense walls of a bubble. In between, where we live, the web is quieter, thinner, and far less crowded. It is the cosmic equivalent of living in the suburban sprawl outside the city, where the traffic is lighter and the skyline is distant. Most of the universe's action is happening somewhere else, far beyond our local horizon. There is something philosophically strange about living inside a void, and it goes beyond the simple fact of low density. A void is not merely a place where things are absent. It is a place defined entirely by what surrounds it, shaped by the gravitational weight of everything pressing in from the outside. The cosmic web does not ignore the voids it creates. It frames them, borders them, and in a very real physical sense, it governs what happens inside them. Everything within the KBC Void, including the Milky Way, exists in a gravitational context set by the massive structures at the void's edges. The filaments and galaxy clusters out at those edges are not passive scenery. They're pulling constantly and relentlessly on everything inside. Our galaxy is not simply floating in neutral space. It is embedded in a gravitational landscape shaped by an enormous hollow region, and that landscape has consequences. The void is not nothing. The void is a structure, and we are inside it. It will be tempting to treat this as an interesting footnote, a quirky detail about our galactic address with no real consequences beyond the novelty of it. We live in the cosmic suburbs, so what, you might reasonably ask? Plenty of interesting things happen in the suburbs, and the universe still works the same way regardless of your zip code. That would be a perfectly reasonable reaction if the KBC Void were simply a matter of local geography with no broader implications. But there is a reason this hypothesis has drawn serious attention from cosmologists who are not easily impressed by local curiosities. Our position inside this vast underdensity may not be a passive fact about where we happen to be sitting. It may be actively distorting the measurements we make of the universe itself. The void we live in could be bending our view of everything else, subtly but significantly, in ways we are only beginning to understand. That is not a footnote. That is a fundamental problem. The measurements in question involve the most important number in modern cosmology, the rate at which the universe is expanding. Every other major calculation in cosmology, the age of the universe, the fate of space itself, the balance of matter and energy, depends on getting this number right. And right now, two independent and carefully constructed methods of measuring it are giving answers that refuse to agree with each other. One method looks at the ancient light left over from the early universe, the cosmic microwave background, and extrapolates the current expansion rate through the standard cosmological model. That method returns a value of roughly 67 kilometers per second per megaparsec. The other method uses nearby stars and supernovae as distance markers and measures the local expansion rate directly in our cosmic neighborhood. That method stubbornly returns a value closer to 73. A gap of 9% between two precise and well-tested measurements is not a rounding error in cosmology. It is a crisis. The discrepancy between 67 and 73 has a name in the scientific community, the Hubble tension, and it has been keeping cosmologists awake for years. Both methods have been checked and rechecked with extraordinary care, using different instruments, different teams, and different underlying assumptions wherever possible. The probability that this gap is simply a statistical fluke, a random accident of measurement, is roughly 1 in several million. That is not a number that allows you to shrug and move on. Something real is causing this disagreement, and the options on the table range from systematic errors in the measurements to genuinely new physics that the standard model cannot currently explain. The standard cosmological model, the framework that has successfully explained nearly everything else about the large-scale universe, has hit a wall precisely here. And the question of whether our location inside the KBC Void is contributing to this tension is one of the most provocative ideas currently circulating in the field. Here is where the void stops being background scenery and becomes the main character of the story. If we are sitting inside a vast underdensity, then the local measurements we make of the universe's expansion are not being made from a neutral, representative vantage point. They're being made from inside a bubble, surrounded by denser regions pulling outward on everything around us. The galaxies in our neighborhood may be moving not only because the universe is expanding, but also because they're being drawn toward the denser walls of the void. Our telescopes would record that motion as recession speed, and our calculations would fold it into the expansion rate without any way to separate the two signals. The local measurement would come out higher than the true global value, not because of any error, but because of where we are standing. The void we live in could be adding phantom kilometers per second to our local ruler. And if that is true, then our cosmic address is not just a curiosity. It is a variable in the equation we forgot to account for. That forgotten variable, the void beneath our feet, leads directly into the strangest measurement problem in modern science. For decades, cosmologists have been hunting one number above all others: the rate at which the universe is currently expanding outward in every direction. This number governs almost everything else we calculate about the cosmos, from its age to its ultimate fate. Getting it right is not optional, not a matter of academic preference, not something you can approximate and move on from. It is the foundation beneath the foundation, the calibration that every other measurement depends on absolutely. Two independent groups of scientists, using two completely different methods and two completely different sets of tools, set out to measure this single number with precision. They expected, reasonably and confidently, to arrive at the same answer from both directions. Instead, they found something that has unsettled the entire field ever since, something that simply should not be possible given how carefully both measurements were made. The first method reaches backward in time rather than outward across space, which is itself a remarkable thing to consider. Scientists trained their instruments on the cosmic microwave background, the ancient light released roughly 380,000 years after the Big Bang. That light has been traveling ever since, cooling and stretching as the universe expanded around it, and it carries within its patterns a detailed record of conditions in the early cosmos. Physicists do not measure the current expansion rate directly from this ancient signal. Instead, they feed the CMB data into the standard cosmological model and extrapolate forward to what the expansion rate must be today. The calculation is sophisticated, the data is precise, and the result is consistent across multiple independent analyses. The CMB ruler returns a value of approximately 67 kilometers per second per megaparsec, meaning that for every megaparsec of distance between 2 points in space, those points are moving apart at 67 kilometers every second. The second method works in the opposite direction, starting close and building outward through a chain of carefully calibrated distance markers. Astronomers begin with Cepheid variables, a special class of pulsating stars whose brightness cycles are directly linked to their true luminosity. Because you can determine how intrinsically bright a Cepheid star is by watching how fast it pulses, you can calculate how far away it must be from how dim it appears in the sky. This technique gives astronomers a reliable rung on what they call the cosmic distance ladder, a sequence of overlapping measurement methods that extends progressively further into the universe. Cepheid measurements are then used to calibrate type Ia supernovae, stellar explosions of such consistent brightness that they function as reliable cosmic lighthouses visible across enormous distances. These supernovae are not perfectly identical in every detail, but their variations follow predictable patterns that allow scientists to standardize them into trustworthy distance markers reaching billions of light years out. When you follow that chain of measurements outward and calculate the expansion rate from what the local universe is actually doing right now, you do not get 67. You get something closer to 73 kilometers per second per megaparsec, a number that sits stubbornly and unmovably apart from the CMB result. Both measurements are careful, both are grounded in solid physics, and both have been refined over years of additional observation and analysis. The gap between them is approximately 9%, which sounds modest until you understand what precision means in cosmology. 9% is not a rounding error in this field. 9% is the difference between two fundamentally different descriptions of how the universe behaves at its largest scale. If two engineers built a bridge using two different measurements of the same river and came up this far apart, nobody would call it close enough and move forward with construction. In cosmology, this gap has a name: the Hubble tension. Think about what this disagreement actually means in concrete terms, because the abstraction can make it feel less serious than it is. The expansion rate is one of the primary inputs used to calculate the age of the universe itself. A higher rate means the universe has been expanding faster, which means it reached its current size in less time, which means it is younger than the slower rate would suggest. The CMB method points toward an older universe, the local method toward a younger one, and the difference between those two ages is not trivial. Ancient stars and globular clusters already push against the lower age estimates, and a higher expansion rate makes that tension worse rather than better. It does not mean the stars are literally older than the universe, which would be physically impossible. It means the numbers are not fitting together the way they should if our model of the cosmos is complete and correct. Something is missing or something is wrong, and the discomfort of not knowing which is very real. The natural first response to any measurement disagreement is to suspect human error, which is both reasonable and fair as a starting point for investigation. Perhaps one telescope was miscalibrated. Perhaps one team made an assumption that quietly introduced a bias into their results. Perhaps the statistical methods used to analyze the data contain a subtle flaw that compounded over time. These are legitimate concerns, and the scientific community took them seriously from the beginning of this controversy. Both the CMB measurements and the local distance ladder measurements have been subjected to extraordinary levels of scrutiny, reviewed by independent teams using different instruments and different analytical frameworks wherever possible. The Hubble Space Telescope, the James Webb Space Telescope, and multiple ground-based observatories have all contributed data to this investigation. The checks have been thorough, the rechecks have been thorough, and the checks on the rechecks have been equally thorough. The measurements have held up under every examination applied to them. The probability that this discrepancy is simply a statistical accident, a random fluctuation that happens to look like a real signal, is approximately 1 in several million. That is a number that effectively rules out coincidence as an explanation and forces the conversation into more uncomfortable territory. 3 categories of explanation remain on the table, and none of them are comfortable to contemplate. The first is systematic error, some unknown flaw in one or both measurement chains that has survived every test applied so far. The second is new physics, some phenomenon operating in the universe that the standard cosmological model does not currently account for, and therefore cannot correct for. The third, and perhaps the most philosophically interesting, is that our location in the universe is distorting our local measurements in ways we have not fully quantified. Each of these possibilities carries significant implications, and at this moment, no one could definitively rule any of them out or confirm any of them as the answer. The standard cosmological model is a genuinely extraordinary intellectual achievement, one of the most successful theoretical frameworks ever constructed in the history of science. It correctly predicts the abundance of light elements formed in the first minutes after the Big Bang. It explains the large-scale structure of the cosmic web with remarkable accuracy. It accounts for the detailed patterns in the cosmic microwave background that satellites have mapped with extraordinary precision. It has passed test after test after test across 60 years of increasingly sophisticated observation. And yet here, at this one specific measurement, the model does not simply underperform. It gives an answer that is measurably, consistently, and stubbornly wrong relative to what direct local observation returns. A framework that explains almost everything has encountered something it cannot currently explain. That is not a minor footnote in the history of cosmology. That is a genuine crisis at the center of the field. What makes the Hubble tension particularly maddening is that both rulers are right in their own domain and wrong only in relation to each other. The CMB measurement is internally consistent and matches the predictions of the standard model for the early universe beautifully. The local measurement is internally consistent and matches what direct observation of nearby galaxies and supernovae actually shows. Neither ruler is obviously broken, neither team has made an obvious mistake, and neither result can be easily dismissed without discarding a substantial body of well-tested science along with it. The tension sits between the two measurements like a wall that neither side can see through, a gap in understanding that is currently one of the most intensely studied problems in all of physics. Careers are being built around it. Papers are being published in rapid succession, and the debate shows no sign of resolving cleanly or quickly. The universe appears to be giving two different answers to the same question, and nobody yet knows which one to trust more. That is the wall the standard model has run into, solid and opaque, and refusing to yield to any of the tools currently aimed at it. And it is precisely here, standing in front of this wall, that the void we've been traveling through this entire time stops being background context and steps forward as a possible explanation. If the local measurements are being made from inside a vast underdensity, if the galaxies around us are moving not only because space is expanding, but also because they're being gravitationally drawn toward the denser walls of the KBC Void, then the local ruler may be reading something real, but misidentifying its cause. The void we live in could be inflating our local measurement of cosmic expansion without anyone having made a single error. It is not a proven solution, but it is a physical mechanism that could explain at least part of the gap. And the possibility that our address in the universe is quietly corrupting our measurements of the universe is one of the most unsettling ideas currently circulating in cosmology. And that possibility that our location is quietly bending the numbers we use to understand everything else demand a closer look. The void we inhabit is not simply a passive backdrop against which cosmic events unfold at a comfortable distance. It is an active structure defined by the gravitational weight of everything pressing in from its edges. To understand why our position inside it might matter, you need to think carefully about what a void actually does to the matter sitting inside it. A void is not a neutral container where physics proceeds exactly as it would anywhere else in the universe. It is a region shaped by the absence of mass, and that absence has consequences that ripple outward in every direction. The galaxies inside the void, including our own, are not floating in a gravitational vacuum where nothing pulls on them. They are surrounded on all sides by the enormous mass concentrated in the dense walls and filaments at the void's outer edges. That surrounding mass is not decorative. It is pulling constantly and with tremendous force on everything inside. Picture a giant transparent bubble suspended in space, its walls dense and heavy with packed galaxy clusters and dark matter threading through everything. The inside of this bubble is nearly empty by comparison, a vast hollow region where matter is sparse and the gravitational field is correspondingly weak. Now place a handful of galaxies inside that bubble, including one that happens to contain a small spiral arm where an unremarkable star has 8 planets orbiting it. Those galaxies will not simply hang there in peaceful equilibrium, balanced perfectly between competing forces. Gravity is the ultimate cosmic tug-of-war, and in this particular contest, the outcome is predetermined by arithmetic. The dense walls on the outside carry overwhelming mass, while the nearly empty interior offers almost nothing to pull back against them. The edges win this contest decisively and completely, and the galaxies inside begin drifting outward toward the denser regions surrounding them. This drift is not random. It is a directed, large-scale flow created by the gravitational imbalance between the void's interior and its massive outer walls. This local flow is where a possible explanation for the Hubble tension might be hiding, quiet and patient and easy to overlook. When our telescopes observe neighboring galaxies and measure how fast they appear to be receding from us, they're recording real, physical motion across real distances. That part is not in question, not even slightly. The issue is not whether the motion is real, but whether we are correctly identifying its cause. According to the KBC Void hypothesis, part of the recession speed we measure in nearby galaxies may have nothing to do with the global expansion of a universe at all. Instead, it may reflect the local flow, the gradual drift of our entire cosmic neighborhood toward the denser walls surrounding the void. We and our neighbors are being pulled outward together, like passengers on the same slow ship being drawn toward a distant shore. Our telescopes faithfully record the motion, but our calculations may be misreading the label on what they have found. The distinction between global expansion and local flow sounds technical, but its implications are anything but abstract or trivial. When astronomers calculate the local expansion rate, they are essentially asking how fast the universe is stretching the space between us and the galaxies we can observe nearby. If those galaxies are also moving toward the void's edges under their own gravitational momentum, their recession speed contains two signals layered on top of each other. The first signal is genuine cosmic expansion, the universal stretching of space that the CMB measurement is also trying to capture. The second signal is local bulk motion, the collective drift of our neighborhood toward denser regions outside the void. These two signals look identical to a telescope measuring recession velocity. There's no obvious seam where one ends and the other begins. If the local flow is large enough, it would add extra velocity to our measurements and push our local expansion rate upward, producing exactly the kind of inflated result that the Hubble tension describes. The scale of this potential contamination is not negligible when you examine the numbers with any seriousness. Relative to the cosmic microwave background, our local group of galaxies is already known to be moving at several hundred kilometers per second in a particular direction across the sky. That motion is real, measured, and accepted by the scientific community without controversy. Part of that motion is attributed to the gravitational pull of known massive structures like the Great Attractor and the Shapley supercluster, dense concentrations of matter that lie in a particular direction from us. But if the KBC Void is real and as large as some estimates suggest, then part of our motion might also reflect the outward drift created by the void's gravitational gradient. A few extra kilometers per second here, a slightly elevated recession rate there, and the local ruler begins reading higher than the global average without anyone having made a single measurement error anywhere in the chain. Here is the part that makes this hypothesis genuinely compelling rather than merely convenient as an explanation. It does not require inventing new physics, rewriting the standard cosmological model, or proposing exotic phenomena that have never been observed anywhere else in the universe. Voids exist throughout the cosmic web. Local flows driven by density gradients exist throughout the cosmic web. The physics involved is entirely standard, well understood, and observed in other contexts at smaller scales across the sky. What the KBC Void hypothesis proposes is not something unprecedented, but something familiar applied at an unusually large scale in an unusually inconvenient location, which happens to be exactly where we are sitting. The mechanism is straightforward. Less matter inside, more matter outside, gravitational gradient pointing outward, galaxies drifting toward the walls, telescopes recording that drift as apparent recession. Each step in that chain follows from basic physics without requiring a single extraordinary assumption. But intellectual honesty requires holding this hypothesis at arm's length rather than embracing it as a solved problem, because it is neither solved nor proven. The KBC Void is a controversial hypothesis, not an established feature of the cosmic map that every astronomer agrees on. Some observational data does point toward a local deficit of matter in our region of the universe, and large-scale flows consistent with the void picture have been detected in certain surveys of galaxy distribution. However, standard cosmological simulations struggle to produce voids of the size attributed to the KBC structure. The same simulations that successfully reproduce the cosmic web at smaller scales find it statistically difficult to generate a void 2 billion light-years across in a universe that otherwise matches what we observe. Different data sets also disagree with each other about how deep the underdensity actually is and how far it extends in different directions from our position. The disagreement between data sets is not a minor technical footnote, but a genuine scientific dispute about the fundamental reality of the structure we are discussing. Some analyses of galaxy surveys find a significant underdensity consistent with the KBC Void picture. Other analyses of different surveys find a much smaller or shallower underdensity that would produce correspondingly smaller effects on local measurements. The size of the void matters enormously here, because a larger and deeper void produces a stronger local flow and a larger contribution to the Hubble tension, while a smaller or shallower void might explain only a fraction of the 9% gap. If the void can account for only 2 or 3% of the discrepancy, the rest of the tension still demands an explanation from somewhere else entirely. The hypothesis is not a single clean answer, but a range of possible contributions whose actual magnitude remains genuinely uncertain and actively debated among researchers who study this question professionally. What the KBC Void hypothesis offers, then, is not a resolution, but a physical mechanism, a specific and testable process that could explain at least some portion of what we observe without requiring the standard model to be fundamentally broken. That is a meaningful contribution to the conversation, even without a definitive answer attached to it. Science rarely delivers clean resolutions on the timescale of a single generation, and the Hubble tension is almost certainly not going to be solved by one elegant hypothesis sweeping all alternatives off the table. More likely, the final understanding will involve several contributing factors, each accounting for a portion of the gap, with the void's local flow being one piece of a larger puzzle that is still being assembled. The honest position is that we are watching an ongoing investigation in real time, with the outcome genuinely uncertain and the stakes genuinely high for our understanding of the cosmos. We are standing inside a vast hollow region of the universe, being gravitationally pulled toward its outer walls by forces too slow for any human lifetime to perceive directly. Our telescopes are recording that motion faithfully and without distortion. Our calculations are interpreting it through a framework that may not fully account for where we are standing when we make those measurements. The void beneath our feet might be adding a quiet bias to the most important number in cosmology, inflating our local ruler in ways that look indistinguishable from a universe that is simply expanding faster than the ancient light of the CMB suggests. Whether that bias is large enough to resolve the Hubble tension, or whether it is only a partial answer to a problem that runs even deeper, is a question that current data cannot yet answer cleanly. And that open question, sitting at the intersection of our cosmic address and our most fundamental measurements, is precisely what makes the next layer of this story worth following carefully. That open question pulls us deeper into the structure itself, past the measurements, and into the physical reality of where we actually live. The Milky Way is not a solitary wanderer, drifting through featureless space with no larger context surrounding it. We belong to something considerably grander than a single galaxy spinning quietly in the dark at the edge of everything. Our galaxy is one member of a local group of several dozen galaxies bound together by mutual gravity into a single gravitational family. That local group is itself embedded within a far larger structure, a supercluster of staggering proportions that astronomers have named Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea contains something on the order of 100,000 galaxies gathered across a region roughly 500 million light-years wide. Every one of those galaxies, every star inside each of them, every planet orbiting those stars, belongs to the same vast gravitational neighborhood. And if the KBC Void hypothesis holds, a significant portion of this entire supercluster may be sitting inside that enormous hollow region we have been discussing. Our cosmic address extends much further than most people ever pause to consider. Understanding why we move the way we do inside this structure requires letting go of a familiar intuition about gravity. Most people instinctively imagine gravity as something that pulls toward a center, a dense point at the middle of a system that everything else orbits or falls into. That picture works reasonably well for planets around stars and moons around planets, where there's an obvious dominant mass at the center of the arrangement. But inside a void, there is no dominant central mass, no obvious gravitational anchor pulling everything inward toward a single point. The center of the KBC Void is defined precisely by its emptiness, by the near absence of the mass that would be needed to create a traditional gravitational center. What governs motion inside a void is not attraction toward a center, but rather the gradient created by everything surrounding it. The dense walls and filaments of the void's outer boundary contain far more mass than the hollow interior, and that imbalance shapes the gravitational landscape in a very specific and consequential way. Think of the gravitational field inside a void not as a bowl pulling everything toward its lowest point, but as a slope tilting gently outward in every direction from the center. Matter sitting inside the void does not experience a strong pull toward anything nearby, because there is very little mass nearby to pull on it. What it does experience is the cumulative gravitational weight of all the mass concentrated in the surrounding walls pressing inward from every side, but unevenly, because the walls are not perfectly uniform and the void is not a perfect sphere. The result is a net drift, a slow and steady flow of matter from the less dense interior toward the denser exterior regions. Galaxies inside the void do not fall dramatically inward toward each other the way objects fall toward a planet's surface. They drift outward, drawn by the gravitational dominance of the massive structures waiting beyond the void's edges. The direction of motion is counterintuitive until you account for where the mass actually is, which is not here but out there, beyond the boundary of our local hollow. This outward drift is not a theoretical abstraction invented to make the hypothesis more convenient. The motion of our local group relative to a fixed cosmic reference frame has been measured, and the numbers are not small or ambiguous in their scale. Relative to the cosmic microwave background, which provides the most reliable fixed reference available to astronomers, our local group is moving at several hundred kilometers per second in a specific direction across the sky. Translated into more tangible units, that velocity works out to roughly 1 million kilometers per hour, a speed that sounds extraordinary until you remember that the distances involved are so vast that this motion is essentially imperceptible on any human timescale. We are not shooting out of the void like something launched from a cannon toward a distant target. The motion is more like a massive ocean current, slow relative to the scale it operates on, persistent across billions of years, and utterly indifferent to anything happening on the surface above it. The ship drifts with the current, and the passengers never feel the movement at all. Part of that motion is attributed to known massive structures lying in specific directions from us, dense concentrations of galaxies and dark matter that exert measurable gravitational influence on our local group. The Great Attractor, a region of enormous mass concentration lying roughly 250 million light-years away, is one of the most significant contributors to our peculiar velocity through space. The Shapley supercluster, even more distant and even more massive, adds its own gravitational pull to the equation from further out. But the KBC Void hypothesis suggests that part of our motion may also reflect the outward flow created by the void itself, the gravitational gradient pushing us toward its edges from the inside. Separating these different contributions to our total velocity is an extraordinarily difficult observational challenge, because all of them are layered on top of each other in the same measurement. Disentangling the void's contribution from the pull of known attractors requires precisely the kind of detailed mapping of the local mass distribution that is still actively underway. The gravitational landscape we inhabit has a second layer of complexity that goes beyond simple bulk motion, and it connects directly to the largest forces shaping the universe's future. Two competing influences govern the fate of structure at the largest scales of the cosmos, and their relative strength in any given region determines how that region evolves over time. The first influence is gravity, the universal tendency of mass to attract mass, pulling matter together into denser concentrations wherever it already exists. The second influence is dark energy, the mysterious property of space itself that drives accelerated expansion, pushing regions of the universe apart from each other at an ever-increasing rate. In dense regions of the cosmic web, where galaxies cluster thickly along filaments and walls, gravity is strong enough to resist the expansion of space locally and hold structures together against the outward push. Galaxy clusters in dense regions can remain gravitationally bound even as the universe expands around them, because the mass involved is sufficient to overcome the separating tendency of dark energy at those scales. Inside a void, this balance shifts in a direction that might seem counterintuitive at first, but follows straightforwardly from the physics involved. The matter density inside a void is significantly lower than the cosmic average, which means the gravitational forces operating within the void are correspondingly weaker. There are fewer galaxies nearby to pull on each other, less dark matter threading through the region to add its invisible gravitational weight, and less overall mass to counteract the expansionary push of dark energy. The expansion of space inside a void therefore proceeds with less gravitational resistance than it would encounter in a denser region. This does not mean dark energy is somehow stronger inside a void, or that it operates by different rules in low-density environments. It simply means that the opposing force, gravity, is weaker there, so the net effect of expansion is more pronounced relative to what you would find in a typical dense patch of the cosmic web. Voids expand more freely than dense regions, and over time, they become progressively emptier as matter continues drifting toward the surrounding walls. This self-reinforcing dynamic means that voids are not static features of the cosmic web, but evolving structures that grow emptier and more pronounced as the universe ages. Matter drains from the interior toward the edges. The edges grow denser as they accumulate that matter, and the interior grows more rarefied in response. The contrast between the void's interior and its surrounding walls deepens over cosmic time rather than smoothing out. A void that exists today will be more extreme in its emptiness a billion years from now than it is at this moment, assuming the standard picture of cosmic evolution is correct. Our local hollow, if it is real, is not a temporary fluctuation that will eventually fill in and disappear. It is a permanent feature of the large-scale structure that is actively becoming more pronounced with every passing billion years. We are living inside something that is, in a very real sense, getting quieter and emptier around us as time advances, even though the change is far too slow for any civilization to perceive directly. That quietude has an interesting consequence worth pausing on, even if it requires holding the idea loosely rather than treating it as established science. Dense regions of the cosmic web are chaotic environments in ways that empty regions are not. Where galaxies cluster thickly together, collisions and mergers between galaxies are common events on cosmic timescales, disrupting stellar populations and triggering intense bursts of star formation. Active galactic nuclei, supermassive black holes consuming surrounding matter at prodigious rates, pour enormous quantities of radiation into the surrounding environment in dense regions where galaxy interactions are frequent. Supernova rates are higher where star formation is more active, and the radiation and shock wave from those explosions can sterilize substantial volumes of space around them. The cosmic web's dense districts are, by any reasonable measure, far more violent and energetically hostile environments than the quieter regions between the filaments. Living inside a void means living in a neighborhood where the most disruptive forms of cosmic activity are happening somewhere else, at a comfortable remove from our particular corner of space. This is a cautious observation rather than a causal claim, and the distinction matters enormously for how seriously to take it. Life on Earth depended overwhelmingly on local conditions, the specific properties of our sun, the orbital dynamics of our planet, the geological history of Earth's surface, and the particular chemical composition of our early oceans. Whether we sit inside a cosmic void or a dense filament probably matters far less to the conditions on any individual planet than the immediate stellar environment does. But there is something worth noting in the fact that our galaxy is located in a region of reduced cosmic activity, a quieter stretch of the universe where the most violent large-scale processes are playing out at greater distances than they would in a denser neighborhood. The void is not the reason life exists here, and claiming otherwise would be overreaching the evidence by a significant margin. But as a backdrop to our cosmic story, the quiet hollow we inhabit is a more interesting setting than a featureless average patch of space would be, and it connects directly to what the universe is about to do next. And that quietude, that cosmic remove from the universe's most violent districts, is itself about to become something far more permanent than we might prefer. Today, we occupy a universe that is almost incomprehensibly generous with its information, its light, its evidence of its own existence and history. By current estimates, the observable universe contains somewhere between several hundred billion and 1 trillion individual galaxies, each one a gravitational city of billions or hundreds of billions of stars. Every one of those galaxies is sending light outward in all directions, and some of that ancient light is reaching our telescopes right now, carrying information about conditions billions of years in the past. We can look at the cosmic microwave background and read the fingerprints of the universe's infancy like text on a page. We can measure the expansion rate, argue about the Hubble tension, and debate the reality of our local void because the universe has left us extraordinary amounts of evidence to work with. That abundance feels permanent and reliable, the way daylight feels permanent when you have never experienced a winter night that lasts for months. It is not permanent, and the universe is already in the process of taking it back, slowly, but with absolute certainty and no possibility of reversal. The expansion of space is not proceeding at a fixed, steady rate that we can simply extrapolate forward indefinitely and expect the sky to always look roughly as it does tonight. The expansion is accelerating, driven by dark energy, and that acceleration has a consequence that sounds almost too strange to be real physics until you work through the mathematics carefully. For galaxies that are already sufficiently distant from us, the space between our position and theirs is stretching so rapidly that the light they emit can never bridge the growing gap and reach us. The galaxies themselves are not moving through space faster than light, which would violate the fundamental speed limit of the universe. Rather, the space between us is expanding faster than light can cross it, which is an entirely different and entirely permitted phenomenon under general relativity. Those galaxies are not disappearing because something destroyed them. They're simply sliding beyond a horizon we can never cross. This cosmological horizon is not a wall you could fly a spacecraft toward and eventually reach if you were patient and fast enough. It is a boundary defined by the expansion rate itself, a limit beyond which no signal, no matter how fast, can ever travel far enough to compensate for the space being continuously created behind it. Every galaxy currently sitting near that horizon is already sending its last light toward us. The final messages that will ever cross the expanding distance before the connection is severed permanently. In the far future, those messages will stop arriving, not because the galaxies stop shining, but because the universe stopped delivering their light to our doorstep. The sky will not go dark all at once in some dramatic cosmic event. It will thin gradually, one galaxy at a time, over timescales so vast that no single civilization could watch it happen from beginning to end. The universe's generosity with information is finite, and we happen to be living during the brief era when that generosity is still close to its peak. The Milky Way itself is not immune to the gravitational dramas playing out in our immediate neighborhood, even as the larger universe slowly empties of visible evidence. Our galaxy and the Andromeda Galaxy, our nearest large galactic neighbor, are currently approaching each other at a speed of roughly 110 kilometers per second across a distance of about 2.5 million light-years. This is not a collision in any sense that would be dramatic on human timescales, But on cosmic timescales, it is an appointment that has already been made and cannot be canceled by any force currently operating in our local group. Standard models of gravitational dynamics predict that these two galaxies will begin their first close encounter in approximately 4 to 5 billion years, passing through each other in a slow gravitational dance that will dramatically reshape both of their structures. Stars will be flung into new orbits, spiral arms will be disrupted, and the two galactic disks will eventually settle into a single merged elliptical galaxy over the course of several billion additional years. The quiet suburban galaxy we inhabit today will be absorbed into something considerably more chaotic before the sun burns out. But that merger, dramatic as it sounds by any reasonable standard of cosmic drama, is actually a relatively intimate and local event compared to what follows it on the timeline of the universe's future. The true isolation, the kind that changes not just our galaxy's shape, but the entire observable context of any civilization living inside it, arrives much later than the Andromeda merger and on a completely different scale of consequence. Over hundreds of billions of years, and then over trillions of years beyond that, the accelerating expansion of space will carry galaxy after galaxy beyond our cosmological horizon, one by one and then in growing numbers. The local group, the small family of galaxies bound together by gravity, will remain intact because gravitational binding can resist the expansion of space at small enough scales. But everything beyond that gravitationally bound island will drift away and eventually vanish from the observable universe entirely, leaving whatever civilization exists here then staring into a sky that grows emptier with every passing billion years. The cosmic microwave background, that ancient and extraordinarily reliable record of the universe's earliest moments, will not survive this process as a useful source of information either. The CMB exists today as microwave radiation filling the entire sky uniformly, the cooled and stretched remnant of light released when the universe was only 380,000 years old. It is already cooler than it was when it was first released, having been stretched by the expansion of space from visible light down to microwave frequencies over the course of 13.8 billion years. As the universe continues expanding and accelerating, that stretching will continue without interruption, pushing the CMB's frequency lower and lower until it occupies radio wavelengths too faint and too long to detect with any practical instrument. The most ancient light in the universe, the same light that gives us our most precise measurements of the early cosmos, will cool into an undetectable whisper and then effectively vanish from the observable record. The universe will have erased the most direct evidence of its own beginning. What remains after that erasure is a scenario that carries a particular kind of intellectual melancholy when you sit with it long enough and follow its implications honestly. Imagine a civilization arising somewhere in that distant future era, billions of years from now, inside whatever merged galaxy remains of our local group after the universe has had its way with the surrounding landscape. These hypothetical scientists are intelligent, curious, and technically sophisticated in ways that would make our current instruments look primitive by comparison. They build the most perfect telescopes their physics allows, instruments of extraordinary sensitivity and resolution, and they turn them toward the sky with the same hunger for understanding that drives every scientist who has ever lived. What they see beyond the boundaries of their own galaxy is essentially nothing. A darkness that extends in every direction without a single point of light from another island universe to suggest that anything else exists. No distant galaxies, no obvious expansion, no relic radiation from a Big Bang, no evidence whatsoever that the universe has a history stretching back further than what their local stars can tell them. These future scientists will not be careless or intellectually lazy. And that is precisely what makes their situation so philosophically haunting to contemplate from our current position. They will apply their best mathematics to the observations available to them. And those observations will be internally consistent and self-reinforcing in ways that will feel completely convincing. Their calculations will tell them that their galaxy is the entire universe, that it has existed in roughly its current form for as long as can be measured, and that nothing beyond its boundaries has ever existed or ever will. They will have no reason to doubt this conclusion, because every piece of evidence available to them will point in the same direction, toward a universe that is solitary, eternal, and unchanging. They will be completely wrong about the nature of the reality they inhabit, and the universe will have made it literally impossible for them to know it. The truth will have been physically erased from the observable record before they ever arrived to ask the question. That future civilization will conduct their science with perfect rigor and reach conclusions that are perfectly false, not because of any failure on their part, but because the universe will have hidden the evidence before they could find it. This is not a hypothetical cautionary tale about the limits of science as a method. It is a straightforward consequence of the physics we already understand, following from the expansion rate we already measure and the properties of dark energy we already observe. The universe does not reveal itself completely to any observer at any location or any time. It shows only what can be seen from a specific position in space, a specific moment in cosmic history, and a specific set of physical conditions that will not last forever. Our window onto the universe's full story is open right now, wider than it will ever be again for any civilization that comes after us. We can see the CMB, we can count the distant galaxies, we can argue about the Hubble tension and the KBC Void and the large-scale structure of the cosmic web. That access is a gift of timing, and it is already beginning to close. And perhaps that is the deepest thing the local void has been quietly pointing toward this entire time, not just a measurement problem or a question about our galactic address, but a reminder about the fundamental nature of observation itself. Every measurement we make is made from somewhere, at some moment, through some window that the universe has opened for us without any guarantee of how long it will stay that way. The void surrounding us may be bending our measurements of cosmic expansion in ways we are still working to understand. The future will inherit a sky stripped of the evidence we take for granted today. And somewhere between those two facts lies the most honest thing science can say about the cosmos. We are seeing only the portion the universe has chosen to show us, from this place, at this moment, through this particular and temporary window. How many other windows have already closed, and how many more are closing right now without our noticing, is a question the universe keeps entirely to itself. That window, the one the universe has generously kept open for us, is already narrowing in ways most people never pause to consider. We live during a cosmically rare moment when the sky is still crowded with evidence, still generous with its ancient light. Every galaxy we can observe tonight is sending us information that future civilizations will never have access to at all. The CMB still hums across the full sky, readable and precise, carrying the fingerprints of the universe's first moments. Distant supernovae still flash across billions of light years, delivering their calibrated brightness to our waiting instruments. The cosmic web still stretches visibly in every direction, mappable and measurable with the tools we currently possess. We argue about the Hubble tension as though the disagreement is a frustration, but the ability to measure it at all is an extraordinary privilege. Our window onto the full architecture of the cosmos is open right now, wider than it has ever been for any civilization that will come after us. That openness is not a permanent condition of the universe, but a temporary accident of our timing. And the void we inhabit has been quietly reminding us of that fragility this entire time. The future scientists we imagine will not be careless or incurious or intellectually limited in any way we could criticize. They will simply be born too late into a universe that has already hidden its most important evidence before their arrival. Their telescopes will be more sensitive than ours by margins we cannot currently imagine, their mathematics more refined, their theoretical frameworks more sophisticated and internally consistent. They will look outward from their merged galaxy into a darkness that extends without interruption in every direction, and they will find nothing to contradict the conclusion that their island of stars is everything that exists. No relic radiation, no distant galaxies, No obvious expansion signal. No thread of evidence pointing toward a Big Bang 13 billion years in the past. Their measurements will be flawless, their logic will be sound, and their final answer will be completely and irreversibly wrong. The universe will have physically erased the truth before they could ask the question that would have led them to it. That erasure is not a malicious act or even an indifferent one, because the universe has no intentions in any direction. It is simply what accelerating expansion does to the observable record over sufficient time. Space stretches, horizons recede. Light from distant sources can no longer bridge the growing gap, and the sky empties one galaxy at a time across timescales no single civilization could witness from beginning to end. The CMB cools from microwaves into radio frequencies too faint for any practical detector to capture, and then cools further still into a background whisper indistinguishable from thermal noise. The most ancient and most informative light in the entire universe does not go dark in a single dramatic moment, but fades so gradually that no generation ever notices the loss directly. What remains after that fading is a cosmos that looks eternal and static and solitary to anyone living inside it. A cosmos that has successfully concealed its own history from every observer it will ever produce after a certain point in time. We are not at that point yet, and the distance between our moment and that future silence is itself worth holding carefully in mind. Right now, we can still read the universe's autobiography in the light it sends us from every direction. We can still disagree productively about whether the KBC Void is real, whether it is large enough to matter, whether it contributes meaningfully to the Hubble tension or only marginally. We can still build better instruments, survey larger volumes of the cosmic web, and refine our measurements of the local mass distribution with each new generation of telescopes. The investigation is genuinely open. The evidence is still arriving, and the question of our cosmic address remains answerable in principle, even if it is not yet answered in practice. That is an enviable position to occupy in the history of any civilization's relationship with the cosmos surrounding it. We are still in the era of discovery, still inside the window, still able to ask questions the universe has not yet hidden the answers to. The KBC Void sits at the center of that investigation, not as a solved mystery, but as a live and contested hypothesis that has earned its place in serious scientific discourse. Some surveys find the underdensity clearly. Others find it smaller or shallower than the hypothesis requires, and the disagreement between datasets is itself informative about the limits of our current observational reach. Standard cosmological simulations struggle to produce voids of the proposed scale, which either means the void is not as large as some estimates suggest, or means our simulations are missing something about the conditions that allow such structures to form. Both possibilities are interesting, and neither can be dismissed without better data than we currently possess. The Hubble tension, meanwhile, persists across every new measurement campaign aimed at resolving it, stubbornly refusing to shrink towards zero the way a simple measurement error would eventually do under sufficient scrutiny. Something real is causing that gap, and the void remains one of the more physically motivated candidates for at least a partial explanation. What makes this moment in cosmology genuinely unusual is that the tension between measurements is not a sign that science is failing, but a sign that it is working exactly as it should. Two careful methods disagree. Neither can be dismissed, and the field is forced to consider possibilities it would otherwise have left comfortably unexplored. The KBC Void hypothesis would not be receiving serious attention if the Hubble tension did not exist to motivate the search for local explanations. The tension created the pressure opened the question, and the question led investigators back to the most fundamental variable of all. Where are we standing when we make these measurements? And how much does that location matter? That is not a trivial question to ask about the universe's most important number. It is the kind of question that occasionally reorganizes entire fields of science when the answer finally arrives. Perhaps the most honest thing to say about our position inside the local void is that it is a perfect illustration of how observation always depends on the observer's location in ways that are easy to forget. We tend to treat our measurements as though they were made from nowhere in particular, from a neutral and representative vantage point that the universe graciously provided for our convenience. But we are not nowhere. We are somewhere very specific, inside a vast hollow region of the cosmic web, being gravitationally drawn toward its edges at 1,000,000 kilometers per hour, measuring the universe's expansion from a neighborhood that may be systematically different from the cosmic average. Every number we calculate about the cosmos is calculated from here, from this particular and possibly unusual address, through instruments that cannot fully separate local motion from global expansion. The void beneath our feet is not just a feature of our galactic neighborhood. It is a variable in every equation we write about the universe at large. And yet, knowing this does not paralyze the investigation or render the measurements meaningless. It sharpens the question instead, points it more precisely at the places where our understanding is genuinely incomplete, and gives future observers a specific target to aim at with better tools than we currently have. The next generation of galaxy surveys will map the local mass distribution with enough resolution to determine whether the KBC Void is as large and as deep as its proponents suggest. Future measurements of the Hubble constant from independent methods, including gravitational wave observations and new distance calibration techniques, will either narrow the tension or sharpen it into something even more demanding of explanation. The cosmic web will be charted in greater detail. The local flow will be measured with greater precision, and the question of how much our address contributes to what we measure will eventually have a quantitative answer rather than a qualitative debate. The investigation continues, and that is the most honest summary of where things stand. The universe never reveals itself completely to any observer, and that is not a flaw in the universe or a limitation of science, but simply the nature of what it means to observe from inside a system too large and too old to be seen all at once from any single vantage point. We see what our position allows us to see at the moment our instruments are capable of seeing it, through a window that is open for a finite and already closing interval of cosmic time. The void we inhabit may be bending our measurements in ways we are still learning to account for. The future will inherit a sky empty to the evidence we currently take for granted. And somewhere between those two facts is the deepest truth this entire journey has been building toward. The universe always shows you only the portion visible from exactly where you're standing, and sometimes a void is not the absence of a story. Sometimes a void is the story. If that idea pulls at something in you the way it pulls at me, subscribe and keep exploring, because the strangest questions in the cosmos are still waiting for the right moment to be asked. How many other windows are closing right now, quietly and without announcement, in parts of the universe we have not yet thought to look? That question has no comfortable answer, and the universe, characteristically, offers none. It simply continues expanding, stretching the light of distant galaxies toward frequencies too long to detect, cooling the ancient fire of the Big Bang toward silence, and drawing the walls of our local void incrementally closer to whatever lies beyond its edges. We measure what